First, math number 6. That says d dt of 2xt squared is equal to 50. And the boundary condition that we're given is that x of 1 is equal to 5. The independent variable is t, the dependent variable is x, and so we're trying to find x as a function of time. There are two ways you can do this. This is the one I like. Substitute z of t, name this new variable 2xt squared, okay? So now this expression, this equation is dz dt is equal to 50. And now we're just trying to solve, find this function z. That's easy to do. So this says dz is equal to 50 dt. So z is equal to 50 t plus some constant. And now, how do you use the boundary condition? There's a couple ways to think about it. One is you know that the boundary condition says when t is equal to 1, x is equal to 5. So you can think of z when t is equal to 1 as being 2 times what x is equal to times what t is equal to squared. And so your new boundary condition is that z of 1 is equal to 10. Okay. So now you can find c. So the boundary condition here, the boundary condition says 10 is equal to 50 times 1 plus c. So c is equal to negative 40. Okay, so your function z then is 50t minus 40. And now you can substitute back to express it in terms of, what you want is x. We invented this z thing, so it's our job to go back now. We have 50t minus 40 is equal to 2xt squared. And so 25, I'm dividing both sides by 2t squared. So you get 25 over t minus 20 over t squared. And that's your function x. Also, maybe possibly more intuitive, instead of doing the boundary condition like this, you might like the feel of it better to, once you find your function z, even before you solve for that constant of integration, substitute back in for x there, and then you can just use the boundary condition like you're used to for x. You'll get the same answer. So we could have done this too when we had z is equal to 50t plus c. Substitute back now, so you get 2x t squared is equal to 50t plus c. I guess you could divide right there. So you get x is equal to 25 over t plus c over 2t squared. And now you can use the boundary condition that says 5 is equal to 25 over 1 plus c over 2 times 1 squared. So 5 is equal to 25 plus c over 2. So c is equal to negative 40. Same thing we got before. And now you can, x of t is equal to 25 over t minus 20 over t squared, just like we got before. It's the same answer. Any questions about that one? You also could do this one by just taking that time derivative. You have to use the chain rule and the product rule and stuff, but then you never have to make the substitution at all. But originally when I made this problem, it was to make you see at least once, remember at least once that you can feel free to make substitutions.
Could you go over number 8 from math?
From math, sure.
Yeah, I got a different answer than you got.
Okay, 5t squared x double dot.
The first thing I did was I divided both sides by 5, which you couldn't do.
5t squared times x double dot, is that right? 50. And the boundary conditions, x of 1 equals 2 and x of 10 equals 20. So I'll write this as x double dot is equal to 10t to the minus 2. And so I'm going to think of it like this, d dt of x dot is equal to 10t to the minus 2. And so that says dx dot is equal to 10t to the minus 2 dt. Integrate both sides, and you get x dot is equal to negative 10t to the minus 1 plus c1. We don't have a boundary condition that we can use at this step, so we have to just carry on all the way through. So now, you know, this is dx dt. So we have dx is equal to negative 10t to the minus 1 plus c1 dt. Integrate both sides, and you get x is equal to negative 10 natural log of t plus c1 t plus c2. This is what you did? So I just forgot to divide something somewhere?
Yeah, I think so.
Okay. All right, so now what do you do with the boundary conditions? Well, we have these two constants of integration that we have to find. So the first one I'll say is x of 1 is equal to 2. So that says 2 is equal to negative 10 times the natural log of 1 is 0. C1 plus C2. Okay, so there's the first equation. And then the second boundary condition says x of 10 is equal to 20. So 20 is equal to negative 10 natural log of 10 plus 10 C1 plus C2. Can someone give me the numerical value of 20 plus 10 natural log 10?
$43.02526.
Okay, so the second one says 10C1 plus C2 is equal to, sorry, say that again, 41 point.
43.
Oh.
All right, do you want me to subtract the 20? So like 20 plus
Yeah, 20 plus 10 natural log of 10.
43.026.
43.026. Okay. And so now that's just a system of equations that you can solve for C1 and C2. One way that we'll talk about this more later, the people who took statics from me, you did it all the time, but if you set this up in an augmented matrix, and this is the first equation and this is the second equation, and you get all the constants on one side and all the variables on the other side. You can fill out this thing called an augmented matrix. So in the first equation, C1 has a coefficient of 1, C2 has a coefficient of 1. The constant is 2. For equation 2, C1 has a coefficient of 10, C2 has a coefficient of 1, and the constant is 43.026. Then run that through your calculator's reduced row echelon form, RREF, and it'll give you a matrix with all ones in the main diagonal, zeros everywhere else. And then, can someone do that for me? Calculate those two values, or?
4.56 and negative 2.56.
And so it gives you these two answers, and those are the answers for C1 and C2 in whatever order you put them in this matrix. So that's reduced row echelon form. It's not that useful for systems of two equations and two variables, but it's very useful if you're trying to solve 10 equations for 10 variables or 20 equations for 20 variables. So I'll talk about that more when we start using it a lot. And then the other one was particle kinematics, number 8, right?
Yeah.
Okay. So this object is moving in the direction that x is increasing along this path, x negative 5x. You can actually, in this case, you can draw what's going on. Okay, so this is a parameterization according to the x position. So what this thing is doing is, if this is the coordinate system, it's following a path like this. Okay? And the speed was 2x.
Doing 5 or 8?
Oh, am I doing the wrong one?
No, it's 8, but you were at 5.
Oh. That's a funny thing to do. I guess because of the negative 5. Okay, so this is 2x. All right. Well, since we have all of our stuff represented in terms of a position variable, it should trigger in your head, we're probably going to use this chain rule approach. So the chain rule approach to finding the acceleration says that we want to, our first, like kind of the starting point to the chain rule is to find the velocity as a function of that position variable. So the question is, can we do that? Yeah, we have the path that's this. And so we can come up with a unit vector that's tangent to that path in the direction of motion. Then all we have to do is multiply it by the speed, this speed function, to give us the velocity. Okay, so first, let's find a vector that's in the direction of this motion. We can do that as, we'll take the derivative of that parameterization with respect to the parameter. It doesn't matter what that parameter is. That's how you do this. So we get 1, negative 5. And if you look at this simple path, that's pretty obvious that that's in the direction of motion. Now we need a unit vector in that direction. And so that is square root, so 1 over the square root of 26, negative 5 over the square root of 26. And now to find the velocity vector as a function of x, we just multiply that unit vector representing the direction by the speed. So we have, the speed was 2x, so we have 2x times 1 over square root of 26, negative 5 over square root of 26. And so, 2x over root 26, negative 10x over root 26. Any questions about that, coming up with the velocity as a function of x? And now we're at the starting point of the chain rule. So the acceleration as a function of x is going to be dv dx times dx dt. And dx dt is the x component of the velocity vector. Okay, so dv dx is 2 over root 26 and negative 10 over root 26. Dx dt is 2x over root 26. And so you get 4x over 26 for the x component, negative 20x over 26 for the y component. Yep.
If we had a position vector in terms of x and y,
Mm-hmm.
can we still solve this?
We're not going to do that in this class, but so yeah, like what if you had let's see, let's say that your velocity vector, you could express it like this. Something like that. The chain rule for multiple independent variables says the way it works is the acceleration would be equal to the partial of v with respect to x times dx dt plus the partial of v with respect to y times dy dt. Dx dt is this, dy dt is this. You can calculate those derivatives, so yes, you could do that. Anybody have any questions about that? We're not going to do any of this multiple argument stuff, but that's how you would do it with something that depended on two variables like that, two position variables. Any other homework questions you want to see? Okay. So last time we started talking about circular motion and spherical motion. I want to start with an example. So let's say that this is your coordinate system. X, Y, Z, and you had an object moving around a circular path like this. And this object moves with a constant speed and completes one revolution per second. And we want to know what's the angular velocity vector. Well, first, the angular speed is, it's making one revolution every second. So this is going to be 2 pi radians over 1 second. So that's 2 pi radians per second. And now we have to think about the direction in terms of the right-hand rule. So it's going around the back toward the front like this. And so your thumb is pointing in the negative y direction. And so this vector is 2 pi times the unit vector 0, -1, 0. And that's 0, -2 pi, 0 radians per second. One thing that might not be totally like intuitively clear. So what I drew there was a circular motion, right? And I defined the direction of the angular velocity in terms of kind of the plane of motion that circle is in. What if it's not circular motion? What if it's spherical motion? So this thing can go anywhere in the plane. How do you define the right-hand rule direction? Yep.
Would you do like a unit vector?
Yeah, but so like if this thing's going all over imagine it being the surface of like a globe, you know? Like, so if it's going in a circle like this, it's really obvious that, okay, your fingers do that, it tells you where your thumb is. But if this is going all over the globe, you know, then what do your fingers do? What does your thumb do, you know?
Wouldn't it have to have like different accelerations to get off of a singular path?
Yeah, that's right, that's right. That's what would be happening. But, so, all I'm trying to get at is, even if something's moving all over a three-dimensional sphere, in an infinitesimal amount of time, it's always going to be carving out the arc of a circle, okay? In the next infinitesimal time, it might be on a different circle on a different plane. But the key thing is, infinitesimally, even if something's going all over the place, you can identify the circle that it's in. And you still, even if it's in spherical motion, at that instant, the right-hand rule determines the direction of that angular velocity. Are you with me on that? Okay. So let me write it like this. Notice, even in spherical motion, over an infinitesimal time interval, the motion is circular. And by that I mean takes place in a single plane. And the meaning of the direction is still the same. As in circular motion. Okay, let's do an example problem. So last time I gave you these equations. They're going to be really important in this class. V is equal to omega cross R. And A, you use the watermelon equation, all.
Right, watermelon.
Yeah, right. All ripe watermelons will rot. And R is the vector from the center of the circle to the object. Okay, these are going to be key equations. So to use these in a calculation, let's say that a child is on a carousel with a radius of 2 meters. At a given instant, it's rotating counterclockwise with an angular speed of 2.5 radians per second. And it's slowing down with an angular acceleration magnitude of 9.5 radians per second squared. Okay, so let's set this up like this. Here's the carousel. The coordinate system, I'll use y-axis up, z-axis this way. And let's do the analysis with the kid here on the carousel. So just in the z direction from the origin. And we want to calculate the velocity vector and the acceleration vector. Okay, so first for the velocity, we know we're going to use this equation. We just have to figure out what these values are. This thing, it's rotating counterclockwise, so this way. the angular speed is 2.5 radians per second. So the angular velocity is 2.5 times a unit vector in the right-hand rule direction. What does the right-hand rule say the direction of this is? Yeah, positive y. Anybody have any questions about that? And so this is 0, 2.5, 0. Okay, so now, well, let's come up with r, I guess, too. So r is the vector that goes from the center of the circle or sphere to the object that you care about. So if this thing has a radius of 2 meters, what's the vector from the center of the circle is where I put the origin. So what's the vector at this instant from the center of the circle to the point? Yeah.
0, 0, 2.
Perfect. Yep. So r is 0. 0, 0, 2. That's in meters. And so the velocity vector is 0, 2.5, 0, crossed with 0, 0, 2. And you get an x component of 5, 0, 0. And now look at the, that's in the positive x direction. Does it make sense that the velocity vector of this point on the carousel is moving in the positive x direction? Yeah, that's perfect. So this cross product thing is going to do all these directions for you. Although it's very helpful to keep the meanings of directions in mind so you can kind of sanity check it as you go. Like, does it make sense that velocity is that way? Yes?
Can we solve this for a generic point on the circle instead of the positive z-axis? But
Yeah.
any direction of the x, z.
I mean, you could do it as
Cosine sine of an
if
angle.
you did it as cosine sine 0, or I guess it's cosine of some angle 0 for y, and then sine of some angle for z. You could do it like that. Times 2, I guess. Yes.
If this was going clockwise, or we were looking
Yeah.
at it upside down, what would change?
If it was going clockwise, the rotation would be this way. And so your fingers would be that way for the right-hand rule.
Negative,
And so, your omega would be in the negative y direction.
but the 2 would stay positive.
Yeah, because that's just, in the coordinate system you're using, that's just the vector from the center of the circle to the point.
Okay. Going out from the origin is always positive. In any direction.
No, if it was on the back side, this would be 0, 0, negative 2.
Got it. Okay.
So these are all positive axis directions. Any other questions? Okay, so now the acceleration. So we also need now the angular acceleration. So what do we know about that? It says that it's slowing down with an angular acceleration magnitude of 9.5. So what does it mean that it's slowing down? What does that tell us about the direction of the angular acceleration? Yep.
Oh, it's negative.
Yeah, not necessarily. Well, so what it really, so here's what it means. In circular motion, so now we're talking about in a plane, if an object, remember I said last time that in circular motion, the angular velocity and angular acceleration vectors are parallel. Okay, that kind of defines circular motion. And if you're in circular motion where those two are parallel, then if an object is speeding up, omega and alpha are going to be in the same direction. And if an object is slowing down, they're going to be in opposite directions. Okay, well, our omega is in the positive y direction. That means our alpha has to be in the negative y direction. So the fact that it's slowing down means alpha is in the negative y direction. So alpha is equal to 0, negative 9.50. Okay, so the acceleration then is 0, negative 9.50, crossed with r, 0, 0, 2. Plus 0, 2.5, this is omega, 0, crossed with the quantity 0, 2.5, 0, cross 0, 0, 2. This one, we already calculated omega cross r. That's how we calculated the velocity. So this is 500. And so all this together is 0, 0, negative 12.5. And this together is negative 1900. So the acceleration is negative 19, 0, negative 12.5. And now let's look, back at the problem and interpret what this is telling us. I said before, this is the tangential acceleration. And this is the centripetal acceleration. So the tangential acceleration is negative 1900. Does that make sense? Well, this thing is moving this way. It's slowing down. So its tangential acceleration has to be opposite the velocity vector. And so that's, the negative x direction. So that works perfect.
Yep, and that's accurate for every point in the circle at that given time.
So to represent different points, what would change is r. So you'd have to do r separately for each individual point, but the same approach would work for any r. So over here, R would be negative 2, 0, 0. Here it would be positive 2, 0, 0. Here it would be 0, 0, negative 2. And then what about the centripetal acceleration? We got that in the negative z direction. That's what we would expect because the centripetal acceleration always goes from the point toward the center of the circle. Okay? Any questions about that? Yeah.
So did you just get the, choose the point like where on the circle you wanted it?
Yeah, I was sort of thinking, imagine that this was given to you. I mean, you have to pick a point. If the problem doesn't give you one, then you have to pick it on your own. But the idea is kind of like the problem would say, okay, this is the point you want to look at.
I guess that's what I don't understand. If I'm on a carousel,
Mhm.
moving at a constant deceleration, then am I not feeling the same effect at every point?
Yeah, right. So at every point, you would be feeling an acceleration opposite the velocity vector. That's the tangential acceleration. And you'd be feeling a centripetal acceleration toward the center. So that's true at every point. But the numerical names for that direction are changing at every point.
But they're both negative and then they cancel, so it's the same. So
Well, like, okay, so let's think of what you would get if you were over here. So in that case, your tangential acceleration wouldn't be in the negative x anymore. It would be in the positive z. You see that? And your centripetal acceleration wouldn't be in the negative z anymore. It would be in the negative x. And if you did all this with an r vector of 2, 0, 0, instead of an r vector of 0, 0, 2, it would make those corrections for you.
Okay.
Any other questions? Yes.
So, will the magnitudes change of these, like acceleration and velocities if they're just moving?
Oh, okay. So in time, they would change if it's slowing down because the angular velocity would change. But at this specific instant, the magnitudes wouldn't change, only the directions. Any other questions? Okay. The next thing we're going to talk about is relative motion, but I think what I'm going to do is, let's just spend some more time on circular motion. This is important stuff. So next class, I'll write some problems up on the board, give you some time to work through it, think through it. Then I'll go through it and you can compare what you did to what I did. Okay. All right. So that's it for today. Yeah.
If that acceleration is constant,
Mm-hmm.
then you don't have that tangential acceleration component. Only a
Oh, if the angular speed is constant, it's staying the same speed?
Yeah.
That's right. Then the tangential would be 0. I mean, it would just be 0 because alpha would be 0.
Yep.
Yeah, right.
yeah, just thinking about that. Like, you don't need to change the point.
So there is directions.